Leetcode skills pristine and truly amazes. This is count vowel strings in ranges. Okay. So you're given a 0-indexed array of strings, words, and a 2D array of integers, queries. Each query, queries I, equals LI asks us to find the number of strings present in the range LI to RI where both inclusive that start and end with a vowel. Okay, so this is a very standard, formulaic, kind of cookie cutter Leetcode data structure algorithm problem asking about ranges and queries in ranges. So you have this initial array, and this initial array has a set of numbers or a set of words or a set of letters, a set of whatever, and the query basically asks for a range within that array, right? From these set of indices, if I cut out the array, the subarray at these set of indices, how many of them meet some filtering criteria, right? So queries LIRI says, I want to cut out, I want to look at the subarray that starts at LI and ends at RI, right? Starts at index LI and ends at index RI, and then determine how many of those words within that range meet this criteria, and the criteria is that the word starts with a vowel and ends with a vowel, okay? And we're going to return an answer, a size queries link. So we're going to look at each query and then determine the number of words within that query range that meet the criteria, and then return an answer for each of the query in an array, right? A parallel array where, you know, the answer to the first queries and the answer to the 0th queries and the 0th index of the answer that we return, the array answer that we return, the answer to the first queries and the first index, and so on and so forth. Okay, so before I even continue this problem and go through the example, since this is such a cookie cutter problem, it should be completely obvious, if you're aware of the data structure and algorithm involved, how to approach this problem efficiently. And that is using the idea of a prefix sum. Okay. If you're familiar with other data structure and algorithms, perhaps not this one, you understand that there are certain problem types where it is obvious from the get-go that you're likely going to use a certain specific data structure and algorithm to approach a problem, right? For example, if you're given a problem where it's asking to find the shortest path between 2 points in a grid, where there's some sort of, you know, obstructing object in the way or whatever, and there's no cost, you know, there's uniform cost across the grid in terms of, you know, going left or right or up or down, it's pretty clear you're going to use breadth first search, right? It's clear that from the way that the problem is stated, from the problem description, that breadth first search is the solution, and it's almost an instantaneous comprehension. Prefix sums with the application to these kind of problems, right? Range problems where you're dealing with, you know, we want to ask a bunch of queries about ranges within an array where a criteria is met. 99% of the time, that's a prefix sum problem. So this is definitely a fundamental data structure algorithm that you need to learn if you're going to be proficient in, you know, technical interviews, data structures, algorithms, Leetcode contests, competitive programming, whatever. And it's interesting because this isn't really taught in school. I wasn't taught this data structure. I wasn't taught this idea in school of a prefix sum. But I found, you know, several problems. It's like every 2 or 3 contests, there's a prefix sum problem, and it's usually one of the easiest ones to complete, because if you know the prefix sum notion, the problem becomes very easy and very simple to spot out. Okay, so with that said, let's look at the example. So we're going to look at the example, solve it, look at a very general, short description of how prefix sums work, apply that to the problem, and then hopefully that's sufficient. Okay, so for the example problem, we have example words equals what? So it's an array. I probably should have pre-wrote this. ABA BCB, ECE, AA, and E. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So when we ask the query 0 to 2, what we're basically doing, so we'll look at each of the query, I guess. I before E except after C. I don't know. Okay. So we have queries 0, 2, 1, 4, and 1, 1. Okay. So when we ask the query about 0, 2, well, it's basically saying for the subarray that starts at 0 and ends at 2, so this whole subarray, how many of these elements, how many of these words meet the condition where they have to start with a vowel and end with the vowel, right? Well, this one starts with a vowel, ends with a vowel. This one doesn't, and this one does. So in total, you get 2. How about 1 to 4? Well, from 1 to 4, we're starting here, 2, 3, 4. So in this range, how many of them start with a vowel and end with a vowel? Well, this does and this does, so you get 3. How about 1 to 1? Finally, 1 to 1. Well, 1 to 1 is just this single element, and there's 0 elements within that range that meet this filtering condition. So the answer is 0. And again, the filtering condition is that it starts with a vowel and ends with a vowel. So this starts with an A, which is a vowel, ends with a vowel, which is an A. This starts with a B, which isn't a vowel, so it's not a solution. This starts with a vowel, which is an E, ends with a vowel, which is an E, so it meets the condition. This starts with an A, ends with an A, meets the condition. This starts with an E, and ends with an E, and meets the condition. Okay, good. Okay, and then these are just the queries that you can do. So technically, the most intuitive solution, if you didn't use a prefix sum, would be to just look at each query range and go from the beginning to the end and add them up, put that in your solution. Look at the next query, go to the beginning, go to the end, add it up, put in your solution. Go to the next thing, add it up, and put in your solution. So that would give you the runtime of n times the length of queries that we'll call m. Okay? Because for each m queries, right, if there's m queries, the query could be the size of the whole array, which is n. So that's n times m runtime. If m is the number of queries and n is the length of words. Words length is 10 to the 5, right? And there could also be 10 to the 5 queries. So that's 10 to the 10 queries. I mean, 10 to the 10 in terms of worst runtime complexity, right? And that's going to be far too slow. It's going to give us a time limit exceeded. Usually around 10 to the 6 or 10 to the 7 is the limit of what is going to get through the autograder. So that's just something to understand, right? If you have a solution, you look at these constraints, and these constraints tell you that it's slower than 10 to the 6 or 7, then it's likely too slow, and there's something more efficient that can be utilized. But not always, but that's a good general rule of thumb. All right. So how do we use this idea of prefix sums to lead us somewhere where the solution is more efficient, right? It needs to be faster than 10 to the 10, obviously. Ideally, it'd be faster than 10 to the 6 or 10 to the 7. That'd kind of be the limit. Well, let's just go off on a little tangent and explain how prefix sums, to think about how we can apply this problem. Right off, if you're watching this, I'm imagining that you either don't know what a prefix sum is, or you have a very insufficient understanding of it, because otherwise, like I said prior, this is one of those problems where it's very obvious that prefix sums is the candidate, and that in the manner of which you would apply and write code to utilize a prefix sum would be pretty intuitive. But that said, let's go off on a little tangent about prefix sums. So how do prefix sums work? Well, prefix sums work well for efficiently calculating sums of ranges, which is kind of what we're doing here, right? So if we had the example, a general array, okay, and this array's value was A, B, C, D, E, and F. Just very general sums of this array. And if we calculated a prefix sum of I, which equals the array at I plus the prefix sum at I minus 1. So this is kind of like your prefix sum recurrence relationship. What would that mean in terms of this array? So if we had prefix sum here, well, the array at I equals, so let's also look at I guess. 0, 1, 2, 3, 4, 5. So prefix sum at 0 would be array at 0 plus prefix sum of I minus 1. Well, there is no previous element. So for the first element, it's kind of like a base case. We just ignore this previous element here. But that would give you A in this spot. So let's move this actually up. Okay. So that would give you just A in this spot. What about prefix sum of 1? Well, prefix sum of 1 would equal array at 1 plus prefix sum at 0. Because it's I is 1, so 1 minus 1 is 0. So array at 1 is B, and prefix sum at 0 is A. So in this spot, you get B plus A. Okay, what about prefix sum of 2? And after this, I think we'll have a sufficient understanding to just kind of populate the rest. Prefix sum at 2 is array at 2 plus prefix sum at 1. So it goes without saying that this has to happen in order, right? You need to populate from left to right so that things are based on previous things that were computed. Very dynamic programming-esque, right? So array at 2 is C, and PS of 1 is A plus B. So that means that I'm going to reorder these things when I add them in. It's a little more obvious. So this is C. This is A plus B plus C. So you notice that every time you go down this list, right, you're just adding the newest element to the kind of running sum that you're calculating. So this becomes A plus B plus C plus D. And this becomes A plus B plus C plus D plus E. Right? And this final one becomes A plus B plus C plus D plus E plus F. So that's what would be in the prefix sum, right? Of course, this would just be one number. I'm just using generalized letters to kind of give you a generalized argument about the nature of how this works, right? But, this would just be like a number here and a number here and a number here, a number here, a number here, a number here. So how can you use this information to do what? Well, what's the purpose of a prefix sum again? It works well for efficiently calculating sums of ranges. Well, if I wanted the sum of the range, for example, I wanted range sum from index 2 to index 5. Well, what would that be? Well, index 2 is C and index 5 is F. So that would be C plus D plus E plus F. So we're supposed to get C plus D plus E plus F. Right? That's the answer that we want to get. And that's what we would get if we just started at 2 and went all the way to 5 and calculated it out, right? But we notice that that's a problem kind of similar to this old solution because we want to efficiently find sums of ranges. So can we do that in constant time instead? Well, how can we find the range sum from 2 to 5 using these pre-populated fields? Well, we're trying to kind of build the puzzle. Like, how can we use these pieces or combination of these pieces to get this sum here? Well, our PS at 5 equals A plus B plus C plus D plus E plus F, right? So this at 5 is close to the range sum at 2 at 5, but we have an additional number of elements, right? We have the C, we have the D, we have the E, we have the F, but what we don't want is the A and the B. So to get rid of the A and the B, well, the A and B is just what's tagged along because we're always summing up what comes before. So if we subtract out PS at 1, well, PS of 1 is what exactly? PS of 1 equals A plus B. Right? Because the prefix sum is like the range sum starting at 0 up until that element. Right? So PS of 5 gives you the range sum from A all the way to F. So we want it from 2 to 5. So we need to remove what comes before 2. So we can just remove what comes from 0 to 1. And then you'll end up with C, D, E, F, which is the idea of what you want, right? Essentially how a range sum, so if you did PS of 5 minus PS of 1, you'd get C plus D plus E plus F, because you'd have A plus B plus C plus D plus E plus F minus PS of 1, which is A plus B, so these A plus B terms go away. The basic idea is generally, right, the general idea is the range sum, I'll call it RS, from X to Y is identical to the range sum from 0 to Y minus the range sum from 0 to X minus 1. Right? Because what I'm essentially saying here is like, using this prefix sum idea, right? What I'm really doing is I'm finding the range sum from 0 to that element. What's the range from 0 to 0? Just A. What's the range from what's the range sum from 0 to 1? A plus B. What's the range sum from 0 to 2? A plus B plus C. What's the range sum from 0 to 3? A plus B plus C plus D, and so on and so forth. So if I want the range sum from any generic X to Y, well, I can just take the range sum from 0 to Y, which I pre-calculated, minus the range sum from 0 to X minus 1, which I've also pre-calculated, which is why that works here, right? To get 2 to 5, all I have to do is take the range sum from 0 to 5, which is PS, the prefix sum of 5, and then to take the prefix sum of 1, subtract those out, and then I get the final solution, the final answer. Yikes. So that's the general idea of using a range sum. So instead of having to populate through the whole array for each range that for each query, I can just minus one thing from another thing, which are two things that are constant because I pre-computed them, right? So instead of having to sum everything from X to Y, I've already summed 0 to Y and 0 to X minus 1. So if I just subtract those in constant time, I can find the answer to this range. So how does this apply then? How does this idea apply to our original problem? Well, our original problem is more or less just a range sum problem, right? 1, 0, 1, 1, 1. Right? These are the values that we're going to sum. This is the value of A and value of B and value of C and value of D and value of E. So if I was to take this system and think about it in terms of a range sum, right? What would words as a range sum be? Well, the first element is 1 because it does meet the condition. The next element is 0 because it doesn't meet the condition. The third element is 1 because it does meet the condition, it does meet the condition, and it does meet the condition. So if we did a prefix sum using this as the array, right? Because what we're trying to do is we're trying to count for the number of words that meet the condition. So if it does meet the condition, we get one additional word that meets the condition. If it doesn't meet the condition, then there's 0 additional words that meet the condition that we're going to return. So what's the prefix sum of this system? Well, it's 1 here. Remember, the next element is just the previous element, so maybe I'll do it in that form, right? It's 0 plus 1 plus right? But this would end up being 0 plus whatever the previous thing is, which is 1. This would be 1 plus whatever the previous thing is, which is 1, so it becomes 2. This is 1 plus whatever the previous thing is, which is 2, so this becomes 3. And this is 1 plus whatever the previous thing, which is 3, so this becomes 4. So now you can efficiently calculate the queries in constant time. So what's 0 to 2? Well, 0 to 2 is just 0 to 2 minus 0 to -1, so this is nothing, right? This is an error. So 0 to 2 would give you a prefix sum of 2, which equals 2. So you have 2 here. What about 1 to 4? Well, 1 to 4 is a little bit more interesting. 1 to 4, using this prefix sum idea, right? And maybe you need to look at this again to kind of think about what I'm doing here, right? But if I want the range sum from 1 to 4, so I'll just put that down here so you can see what I'm saying. If I want the range sum from 1 to 4, well, that's just the range sum from 0 to 4 minus the range sum from 0 to 0, right? Because I'm 1 to 4, x is 1, y is 4, so 0 to 4 minus x minus 1, 0 to 0. And how do you get this? Well, this is just prefix sum of 4, and 0 to 0, that's just prefix sum of 0. So if I subtract prefix sum of 4 from prefix sum of 0, I should get the solution from, in constant time, from 1 to 4. So that would be prefix sum of 4 is 0, 1, 2, 3, 4, which is 4. 4 minus 0, which is 1, which gives you 3. So then this one becomes 3. This one's 2, of course. And then 1 to 1, would that be from 0 to 1 minus 0 to 0. So that would give you 0 to 1 would be 1, and then 0, 0 would be 1. So 1 minus 1 is 0. So this would become 0, right? Because from 1 to 1 would equal 0 to 1 minus 0 to 0, just using this formula directly. And prefix sum of 0 to 1, that'll just be prefix sum of 1 minus prefix sum of 0. These both equal 1 in the case above, so it equals 0. Okay, and that's how you can officially do it. So now you just have to look at each query, and then for each query, you do a constant operation, right? So you have to look at all n words to populate the what? To populate the prefix sum array, and then you have to look at all queries, but for all queries, you just do a constant operation. So it's n words we have to look at to find the prefix sum, and then we have to look at all m queries, but for all m queries, we no longer have that n factor. So this is 10 to the 5, and this is 10 to the 5, 10 to the 5 plus 10 to the 5, 2 to the 10 to the 5 in terms of big O runtime, that's just 10 to the 5. So that's 2 times 10 to the 5, I mean, in terms of the number of computations is fine, right? We said 10 to the 6 is the limit, so we're good. Okay. So, kind of in summary, what did we do? Well, we looked at words and queries. We noticed that this problem is pretty obviously a prefix sum problem. We looked at how a prefix sum works by efficiently calculating ranges, and then we modeled our words array in a manner of a prefix sum, and then utilized the prefix sum idea to efficiently calculate the queries. So with that said, let's go ahead and get right into the code. So for the prefix sum array, I'm just going to use a default dict because it's going to be a little bit easier. And then we're going to have to look at each word in words. Well, we need to know the index. So index in word and enumerate words. Well, the prefix sum at this index equals the previous prefix sum, right? So basically what happens is, well, the prefix sum at some index, right, like here, is the previous one plus if this word meets the condition, then it's a 1. What would it mean for the word to meet the condition? That would mean that the word starts with a vowel and ends with a vowel. So we could basically just say, we'll create a vowel set here. Let's call it V, whatever. A, E, I, O, U. So we'll say if it's in the previous index, and if it's the case where the word 0 is in V and the word at the last letter is in V, right? So we're basically saying the number that meet the criteria up to this point, right, is, well, whatever from 0, right? The number of elements that meet the condition from 0 up to this index is whatever is the number of elements that meet the condition from 0 up to the previous index plus 1 if the current word meets the condition up to this index, right? So basically going through this, it's like, okay, there's 0 to the left, but since I meet the condition, it becomes 1. At this point, there's 1 to the left, but I don't meet the condition, so it's still 1. At this point, there's 1 to the left, but I meet the condition, so now it becomes 2. Right? So that's all that's happening here. Just a concise way of doing that. And I guess we could put it on one line. All right. And then now what we have to do is we just have to look at each query. So how does the query work? Well, for query XY, right? For query XY, we just do the range at 0 to Y minus the range from 0 to X minus 1. So for a query generally, I guess a query XY, in terms of the prefix sum, that's just the prefix sum at Y minus the prefix sum of X minus 1. All right, that's what we did here, right? From 1 to 1, it was prefix sum of 1, which was Y, and 1 minus 1, which is 0. Maybe that one's a little, okay. 1 to 4, right? 1 to 4 is just the prefix sum of 4 minus the prefix sum of 1 minus 1, which is 0. Okay. So we'll do XY, I guess, because that's kind of the language we use. So we'll do prefix sum of Y minus prefix sum of X minus 1 for XY in queries. Okay, cool. So this is definitely one of those problems that you should pretty quickly understand if you know the trick, which is the prefix sum. If you don't know what a prefix sum is, don't blame yourself for not knowing how to solve this problem. This is exactly why we're watching videos. This is exactly why we're covering problems. This is exactly why we practice, because often it isn't the case that someone else is more intelligent than you when it comes to solving these problems. It's typically the case that that person just has exposure to that kind of problem previously, so they know what they need to do, right? Because these things aren't intuitive in terms of, you know, you sitting down and figuring out how things work. These things are intuitive in terms of, oh, this is similar to something I've done before, and this is how you approach that efficiently, right? These aren't things you do in your daily life, so don't beat yourself up too much if it's not always completely obvious, right? Okay, so with that said, what is the run and space complexity? So let's say n is the length of words, and let's say that m is the length of queries. Well, we have to look at all words to populate this prefix sum array, right? And it's a constant operation. You might say, well, doesn't the length of word matter? No, because we only look at the first letter and the last letter of word. So if the word is 1,000,000 characters or 2 characters or 1 character, we only look at the first letter and the last letter to make a decision about whether or not it meets the filtering condition. So this is a constant operation independent of how long the word is, and this is a constant operation. So we look at all n words and we do a constant operation. So we only do n operations to populate the prefix sum, but then we have to look at all m queries, right, to return the answer to each of those queries. But for all m queries, this is a pre-populated value, so that's constant. This is a pre-populated value, so that's constant. So this is n time to populate the prefix sum and m time to find all the queries. So that's time complexity, big O, of n plus m. Okay, and then what about space? Well, it's the same deal, because we have to populate this prefix sum for each of the words. So there's n words, so I populate n indices or n keys of this default dict. And then there's m queries that I have to execute upon. And for all m queries, I need to save that information to return it to the user. So I have to look at all n. I have to populate n word indices for prefix sum, and I have to return all m found query answers. Okay, guys, have a beautiful rest of your day. I'll see you tomorrow.